So I'd like you to pause this video and try to fill this in on your own using the same routine that we did on the last one. So you should first evaluate g of -5. That means plug in -5 for every x in g of x. When you do that, you should get -1 for g of -5. Then you should take what you got for g of -5, which was -1, and plug it in for every x in f of x. This gives you -1 squared, which is 1, plus 2, which is 3. So f of g of -5 should be 3. For g of f of -5, you should first be evaluating f of -5. Plugging in -5 for every x in f of x should give you 27. You should take that answer and plug it into g of x for every x. So you're now evaluating g of 27, which is 31. On the first page when we were doing compositions of functions, we only used this notation, f of g of x, and that's function notation, but this is another notation that is the same thing. So f of g of x is the same as f of g of x. They both have the same meaning. They both say plug in g of x for every x that you come across in f. So go ahead and pause the video and see if you can successfully come up with f of g of x, plugging in g of x for every x in f. Hopefully you started out with x plus 4 squared plus 2. That's just plugging in g of x for every x in f. Then you need to simplify that. Remember, x plus 4 squared is not just squaring both terms, it's actually multiplying it out, multiplying x plus 4 times x plus 4. Remember, we have to FOIL that out. We don't just square both terms. So we end up with x squared plus 8x plus 16 when we FOIL that out, and then we can't forget to tack on that plus 2 on the end. Okay, when we combine like terms, we get x squared plus 8x plus 18. That is our final simplified answer for f of g of x. Now go ahead and pause the video and see if you can do g of f of x. Okay, so when you first plug it in, you should have plugged in f of x for the only x in g, which should give you x squared plus 2 plus 4. Then combine like terms and simplify it, and you get x squared plus 6. Okay, so remember on the previous page when we were finding the domain of a composition of functions, we had to look at the input. In this case, the input is g of x. If you look up at the top of the page, g of x was x plus 4. That's a linear function. So the domain, like on every linear function, is all reals. Okay, then the result, that was the final answer that we got. The result was a specific kind of polynomial function. Hopefully you all recognize it from our last unit. It was a quadratic. What's the domain on every single quadratic function? Do we remember this from last unit? The domain was all reals. So in this case, the domain on the input and the result was all reals, which means that the domain on the composition of functions is also all reals. If we look at the other composition of functions, g of f of x, the input function, the input f of x, that was x squared plus 2. What kind of a polynomial function is that? That's a quadratic. So domain is all reals. And the result that we got, x squared plus 6, is also a quadratic. And its domain is also all reals. Since they're both all reals, that means that the domain of our composition of functions is also all reals. Okay, so the last thing I want you to do is try to evaluate f of g of negative 5 using the composition of functions we came up with, and g of f of negative 5 using the compositions that we came up with. Hopefully, when you did f of g of negative 5, you plugged in negative 5 for every x in f of g of x, which should have given you 25 minus 40 plus 18, which is 3. Notice f of g of negative 5 should match the f of g of negative 5 that you got up at the top of the page. For g of f of negative 5, you should have taken g of f of x, which we found up above was x squared plus 6. You should have plugged in negative 5 for every x. There was only one to plug in for. Gotten 25 plus 6, which is 31. That answer should match what you got up above when you plugged in f of negative 5 first and then plugged that into g of x.